We're now going to make predictions or recommendations about what to do when you interact with someone else for which you only have a minor conflict. So here I'm going to describe a situation, I'm going to distill it into its strategic form, and then analyze it like we've analyzed the previous problems where we've had either perfect or major conflict. So consider a format game for the Blu-ray Disc Association and Toshiba, these two players here. And they, at the same time, so simultaneously, have to adopt either the Blu-ray format for their DVDs or the HD format, Blu-ray HD, Blu-ray HD. If they both adopt the same format, then they both gain 100 million from customers that value the convenience of having a universal format. Suppose if they both choose Blu-ray, then the Blu-ray Association gains an extra 10 million. And if they both choose HD, Toshiba gains an extra 10 million. So predict or recommend strategies. Let's write the payoffs here in millions of dollars. If they choose the same format, either both Blu-ray or both HD, they'll each gain 100. And then there's an additional 10 million to the Blu-ray Association if they're both choosing Blu-ray. And there's an extra 10 million to Toshiba if they both choose HD. So that's the payoff table. Now, about that table, is there a dominant solution? Well, there's no dominated actions, and all actions are rationalizable, so there's no dominant solution. Now, is there a Nash equilibrium? Well, let's see. This, you'd want to switch rows or columns. This, you'd want to switch rows or columns, so it's neither of these, but this is a Nash equilibrium. Do you see how they could potentially agree to both play Blu-ray, and neither one of them would have any reason to cheat? By switching columns, you'd get worse. By switching rows, you'd get worse. Also, there's another possibility, is that they both choose HD. There's no reason for them to cheat each other if they were to both agree on this. So there's two Nash equilibrium choices. Now, is there a mixed strategy solution? So a third possibility. And we're going to be computing this the same way we computed when there was major or perfect conflict. We're going to compute the mixed strategy solution that stops the other player. We're going to call him the opponent, but maybe we really shouldn't do that because the interests are not in conflict. What would stop the other player from exploiting his knowledge of your actions? So we're going to be computing these mixed strategies in the same method as we used before. So for the Blu-ray Association, suppose that Toshiba predicts that the Blu-ray Association will pick Blu-ray with probability P and HD with probability 1 minus P. That would give Toshiba a payoff of 100 with probability P for this first column and 0 with probability 1 minus P. And that's for the first column. For the second column, 0 with probability P and 110 with probability 1 minus P. And if you equate those, you would get that P is equal to 110 over 210. And then we can plug that into either equation and determine that Toshiba has an expected payoff from either column of 52.4, and that's in millions of dollars. Likewise, suppose the Blu-ray Association predicts that Toshiba would pick the first column with probability Q and the second one with probability 1 minus Q. These probabilities are chosen so that player 1 cannot exploit their knowledge of those probabilities. And what that means is that the expected payoff from the first row is the same as the expected payoff from the second row. From the first row, you'd expect 110 with probability Q and 0 with probability 1 minus Q. And then from the second row, you'd expect 0 with probability Q and 100 with probability 1 minus Q. If you equate those, you get that Q is equal to 100 over 210. Plug that into either equation, and you get expected payoffs of 52.4. Now, in conclusion, there are three possibilities for what happens, and either they both definitely are here, they are both definitely here, or you have a mixed strategy. Now with the mixed strategy, you get an expected payoff of 52.4. That is worse for both players than if they would have chosen either of the two Nash equilibrium. And the reason for this is that the mixed strategies are not optimal because they're designed so that your opponent would not benefit from exploiting his knowledge of your actions. And what hurts him hurts you too in this case, because now your interests are mostly in alignment, because your interests are mostly aligned with the other player. So instead of calling him an opponent, when your interests are aligned with another player, you should call them your ally. And you want to be predictable to your allies and unpredictable to your opponents.